Okay, so we're going to begin in just a minute or so as people wander in. I feel like I should be running down the aisles, getting people, yeah, come on. All right. Okay, welcome to Grid Streets and Pipelines, building a linguistic street map with scikit-learn, probably one of the longest titles of some of the talks today. This is Michelle Fullwood, and I'll let her do her thing. So we may or may not have time at the end of the talk for questions and answers. If we run out of time, you can direct your questions later on in perhaps an open space. Thanks.
Thanks. Okay, so let me start with introduction. So I'm a grad student in linguistics. I love languages and maps. I also happen to be from Singapore. And if you ever go to Singapore, you might observe that the street names there display an astonishing linguistic diversity, reflecting the diversity of races and ethnicities among the people who immigrated to Singapore following the British founding of a port there in 1819. So alongside names from the indigenous Malay community, like Jalan Besar on the top left, we also have names from the British colonists, so like Northumberland Road. There are also names from South China, like Keong Saik, South India, like Veerasamy, and many others. So for example, Belilios is a Jewish name. And then, of course, you have these generic names like Racecourse Road. But while the road names are diverse, they aren't homogeneous. So there's lots of little clusters of road names of similar linguistic background. So for example, here we see a British cluster. So we have names like Cambridge, Carlisle. And what I wanted to do in this project was to have an easy way of visualizing these clusters. Something like this, where every road name is color-coded for linguistic origin. And I wanted to do this for the whole of Singapore in as automated a fashion as I could. So what ingredients do we need to make a linguistic street map? So we need the geographic locations of the roads. I got this from OpenStreetMap, which is an openly licensed volunteer project to create a map of the world. Has pretty good coverage in Singapore. We also need linguistic classification of each road. So what I decided to do for this is to do some machine learning with scikit-learn. So let's get started. So the goals for this talk, so I'm going to spend most of the time talking about how to do classification with scikit-learn. We're going to build a baseline classifier, and then we're going to talk about how to add features and organize them using pipelines, how to improve performance by tuning hyperparameters. And the rest of the talk, I'll be talking about how to wrangle geodata using a library called geopandas and how to plot a map. So where I downloaded the data from, there's this useful website that basically gets together the OpenStreetMap data for particular metro regions around the world. Singapore is one of them. I downloaded the data in GeoJSON format. This is what it looks like. Basically, we have these dictionaries of properties, and most importantly, we have the geometry, which could be a point, it could be a line string, could be an area. And these would be coordinates of lats and longs. So it turns out that if you want to do pandas-style wrangling with GeoJSON, pandas doesn't actually open this GeoJSON file because it's organized in this dictionary format. But luckily, there's this really useful library called geopandas that will. So what geopandas does is it extends pandas and incorporates a whole bunch of little geographic libraries from around the Python ecosystem. So geographic data manipulation, geographic file input, output, and really makes life a lot easier for us when we're dealing with such data. So for example, reading in a GeoJSON file is as easy as gpd.read file. How it organizes the data will be as a geodata frame. So this is an exact analog of the data frame in pandas, except that there's going to be a special column for geometry. So we've read in our Singapore roads file, and what we see is that it's 60,000 roads long. This seems a little bit suspect, so it would be really nice to see what's going on in it. It's really easy to plot stuff using geopandas. We just call df.plot, and it gives us this matplotlib plot of all of the stuff that's in your data frame. So looking at this, we can see why there's so many extra roads. When Metro Extracts took their extract, they did a bounding box around Singapore that wasn't, that includes parts of Malaysia and Indonesia. So we need to get rid of all those roads that aren't actually within the Singapore administrative boundary. So GeoPandas makes this really easy as well. So what we want to do is to take our initial data frame and filter it to just the roads within the administrative Singapore boundary, which I downloaded a data file for that's called Singapore here. And all we have to do is just filter the roads in df to those where df.geometry lies within the Singapore.geometry. And we see that that did what we wanted. So GeoPandas made this really painless. And since GeoPandas is based on pandas, all of the usual pandas operations that we're used to are still available. So we can filter out empty road names using not null. We can accept roads only that are within a list of accepted road types. So we can leave out things like footpaths and stuff like that. So after a whole bunch of data cleaning, what I had for classification was this. So I divided the road names up into the actual name, as well as what I call a road tag, so things like road, drive, park, crescent. And now we're actually ready to start classification. So building our baseline classifier. The ingredients we need here are a classification schema. We have to decide what categories we want to classify our roads into. We're going to be doing supervised classification, so we're going to need a labeled train and test set. So when you're doing machine learning systems, they don't really know what strings are. We need to find some way of transforming our strings into something, into numerical and Boolean features, which a machine learning system can actually understand. And then we're going to need a classifier and an evaluation metric. So this is the classification schema I went with in the end. You see that it exactly mirrors the categories that we saw in the very beginning. And how I did the labeling was this. So I divided up the data set into 10, and I hand-labeled the first 10% of the data. And then what I did was that I built a training. I used that for as the training set of a classifier, and I used that to classify the next 10%. And then I went through and hand-corrected that, and then I used the first 20%, which is now verified correct, as the training data for the next 10%. And the reasoning behind doing this was that, well, as we add training data, our performance should start to increase, and so there'll be less work involved in hand correcting each subsequent 10% of the data. So that was the idea. But let's say you had a whole bunch of data that's already labeled, and you want to split it into training and testing. So scikit-learn provides a function for doing this called train test split, and this is how it looks. The next step is to choose what features we're going to use. So what I went with was calculating the n-gram frequency. So n-grams are basically just contiguous sequences of, in this case, characters of length n. And we're going to calculate these in an overlapping way. So unigrams or 1 grams are just characters. So here, there's 2 of each letter except for the hyphen. Bigrams are going to be sequences of length 2. So we have one of the start symbol followed by an M, and 2 of just about all of the others, except for the ones around the hyphen and around the N. And the same thing for trigrams. Why choose n-grams? So n-grams are a really good feature to use in distinguishing between languages, because different languages have different patterns, different typical sequences of letters. So for example, if we look at row names that contain the bigram CK in our data set, we see that there's 23 such roads that are British, and 17 that are Chinese, and 0 that are Malay or Indian. So the next time we see a road that has the bigram CK in it, we can say with pretty high probability that it's not Malay and it's not Indian. It's probably going to be British or Chinese. Okay. So how do we extract n-grams? Again, scikit-learn provides a really useful tool for this. It's called count vectorizer. And so what we do is we initialize our n-gram counter, and we tell it what the range of n-grams we want to calculate is. So here I'm going all the way from 1 grams to 4 grams, and I'm telling it that I'm doing it on a character level. And then what we do is that you take this object that we've just instantiated, and you fit transform it to data train. Data train here is just our list of row names. And what you're going to get back is a feature matrix of all of the n-gram frequencies for each road. And then we do the same thing for the test data. So this is the list of row names in the test set. But instead of calling fit transform on that, we just call transform. So we have a similar feature matrix for that. OK, next step is selecting a classifier. So scikit-learn provides a really nice cheat sheet for deciding what sort of classifier to start off with. So we could just work through this. So starting for start, do we have more than 50 samples? Yes. Are we predicting a category? Yes. Do you have labeled data? Yes. And do we have fewer than 100,000 samples? Definitely. So it's suggesting that we try linear SVC. So what exactly is linear SVC? So basically, let's pretend that we're doing binary classification now, and we have 2 features. So we're classifying things into whether they are red crosses or blue dots. And we're plotting them along, based on along these 2 axes of like feature 1 and feature 2. And it so happens, because this is an idealized data set, that it falls into 2 linearly separable categories. So it makes sense to sort of draw a line up it and say everything that's below this line I'm going to say is a red cross. Everything above the line is going to be a blue circle. But you can see that there's many different lines that are going to fit. So which one are we going to choose? So in linear SVC, what we choose is the line that gives us the maximal margin between the 2 data sets, like in this picture. And once we've done that, the next time you have unknown points, you just classify them based on where they lie with respect to the line. OK, so that's linear SVC. What's the code look like? So we just initialize a classifier as linear SVC, and then we fit a model based on the training feature matrix xtrain and ytrain, which is our list of actual road labels. So this would be a vector saying, first road is British, second road is Chinese, et cetera, et cetera. All right, so now we have our model. And we want to test how well it does. So we need to select an evaluation metric. And scikit-learn comes with a bunch of evaluation metrics built in. And each one is useful for different purposes, depending on what you're trying to optimize. So in my case, what I was trying to optimize was I wanted to spend as little time as possible having to do hand corrections. So it made sense to go with accuracy score, because I wanted to have as many correct as possible. So So we apply our model to our X feature matrix, our test feature matrix, X test. For that, you do model.predict. And what you're going to get out is the classifier's best guess of the road label for each road. And we're going to store that in y-test. And then we just need to call accuracy score on y-test versus what the actual values were. And on 10% of the data, I got 55% accuracy. So that's where we are now. So you might look at 55% accuracy and think, well, that's pretty close to chance. Well, not quite, because we have 6 categories that we're choosing between. So true chance is actually at 16.6%. Another thing we could do is to write a really dumb classifier that says, all of my roads are Malay. Like, no matter what road name you give me, I'm going to tell you it's Malay. And because Malay is the most frequent linguistic origin in the data set, that 35% of the roads are Malay, it's going to be right 35% of the time. So this is our sort of lower bound. For the upper bound, it would be nice if we could get 100% accuracy, but based on my experience and when I was actually doing the hand correction, the hand labeling, I found that I needed to look up about 10% of the roads because I personally wasn't sure, whether it was Malay or Chinese just by looking at it. And I figured that the computer probably isn't going to be able to do that either. So our likely upper bound is going to be 90%. So 55% isn't terrible, but it still means that I had to hand correct about half of the data set. So let's see how we can improve it. So ideas for improving the classifier. So one thing we can do is to just add more data, but we're trying to avoid work if at all possible. So we're not going to do that first. Another thing we can do is to try other classifiers. So scikit-learn makes it really easy to drop in classifiers and just swap them out because there's a standard API for all of the classifiers. So I'm not going to talk about that. Another thing we can do is to add more features. And the fourth thing we can do is to try hyperparameter tuning. And there's other things we can do, but I'm just going to talk about the last two. So adding features. So doing feature engineering. Let me start again. So there's this really useful paper that I recommend everyone interested in machine learning read by Pedro Domingos, which is called A Few Useful Things to Know About Machine Learning. And in it, he talks about how feature engineering is the most important part of the project. And this is where most of the effort in a machine learning project goes. So, basically, this is the section where we're doing the most experimentation, adding in features, taking out features, scaling features, just trying to see what works best. And what we want to do is to find features that are as discriminative between the different categories as possible. So some features that I thought of adding were the number of words in a road name. So for example, Chinese road names tend to have either 2 or 3 words in them, whereas the British road names or Indian road names tend to have just 1. So it's discriminative in that sense. Average length of words. So the Chinese road names tend to be monosyllabic. So they tend to be a lot shorter than, say, the Indian road names, which tend to be, 3, 4, 5 syllables long. Are all the words in the dictionary. So this is meant to discriminate between the generic category and the British category. So both of them are sort of English words, but only most of the generic words will be in the dictionary, whereas most of the names will not. And the last one is the road tag Malay. So a lot of Malay road names in Singapore don't use street and road as their road tag, but they're Malay equivalents like Jalan and Lorong. So this was a really good estimator. All right. So let's think about how to add those features. So this is actually the code from before when we were doing the n-gram feature extraction. And you can see that we had to do a few things. So after initializing the count vectorizer, we had to call fit transform and transform on the training and testing data. And you can see how, as we add features, it gets a little bit of a drag to keep on having to call these functions on the train set and the test set. It's a little bit repetitive. You can imagine if you're doing 40 of these, then you just have 160 lines of of this very repetitive code. And because in the course of feature engineering, you might be commenting out some of these, and then you have to remember, oh, did I comment this out in both the train set and the test set? Did I scale this in both the train set and the test set? So there's actually an easier way to do this, which is to use pipelines. And in pipelines, the idea is to just conceive of our steps as taking place one after another, each one transforming the output of the previous step. So our pipeline here is just the n-gram counter followed by the linear SVC classifier. And we can put this into code like this. So we're going to import pipeline from scikit-learn.pipeline. And we're going to initialize the two steps within this pipeline and give them labels, n-gram and CLF. And once you've done that, no longer do we need to do the fit transform and transform on the intermediate steps. All we need to do is at the end call pipeline.fit on the data.train and the y.train to get our model. And then we just, from there we just do prediction. So no matter how many steps there are in between, you only ever have to do one pipeline.fit at the end. So that's really convenient. So let's talk about how we can add a new feature to this pipeline. So let's say the average word length feature. So what we need to do is to define a new data transformer that takes in a data frame, extracts out the row names, and outputs the average word length. And here's a schematic for how these transformer classes look. So we're going to inherit from base estimator and transformer mixin. And it's going to there's usually an init function if you need it. And there's going to be a fit function, a fit method, which usually does nothing and just returns self. And the other crucial function that you need to define is transform. And this is the one that actually does something to whatever is coming in.
So, Michelle, we just have about 5 minutes left.
Oh, OK. So writing our own transformation class. So now we're doing average word length extractor. So again, fit does nothing, and transform takes the row names and applies this function that just computes the average word length to them. So that's what that looks like. And we want to add this to the pipeline, but we don't actually want to. We can't actually just add it to the existing pipeline because we're not actually doing this in serial. We're doing this in parallel. So how we do this is to do a feature union. And feature union basically just, so basically it looks just like pipeline, except that it's going to do the things in parallel. Yeah. All right, so what happened after we added the features? We got up to 65% accuracy. So just to summarize, I wanted to emphasize that using pipelines and feature unions does not improve performance in and of itself. They're just a great tool for organizing the code readably, allowing for easier experimentation. All right, hyperparameter tuning. I have to go through this pretty fast now. What are hyperparameters? So when we call linear SVC, what we're actually doing is there's a whole bunch of defaults that are actually already set for us. And these are pretty sensible defaults. But changing the values of these parameters can alter the performance, sometimes quite significantly. And what it would be nice to do is to be able to try a whole bunch of different parameters. And this is what GridSearchCV does. So it basically tests every single one of these and tries to and just sees which one worked the best. And as you can tell, as you add options and add dimensions along each option, we're going to we're exploring a really big space. So this is just something to keep in mind when you're doing grid search. And doing grid search is really easy, so we're going to define a parameter grid, and then when you do GridSearchCV with your pipeline, and then you just do grid.fit to your x and y, and that gives you your best parameters. It tells you what your best score was. And 70%, can we say that this is the new best score? Well, not quite, because it's the best score on the training data. We still need to test it. So what we do is we call our new estimator is going to be grid.bestestimator, and we fit that to data.train and ytrain. And then we just do the usual thing, and we got 68%. So I wanted to talk about which hyperparameters to choose, but I don't think I actually have the time to do this. Basically, it's usually the top few parameters in the documentation, and I also recommend these papers. You can also look on GitHub to see what other people did, and yeah, and I'm going to post the slides later so you can read the summary. All right, so let me just do making the map in 2 lines of Python. So what we do to create the map is just to plot the map, but this time we plot the data frame, but this time we pass a column classification, and what that does is to color code things according to classification. And then we can convert this into an interactive leaflet web map using MPL leaflet. And yeah, and basically you can zoom in, zoom out, and pan. And we did all this in just 2 lines of Python. So yeah, that's it. Thank you.
Great. Thank you, Michelle. I think we might have time for 1 or 2 questions, if we have any from the audience. If you do have a question, again, just please keep it short, just in the interest of time. But if you could step up to the microphone, that would be great.
Hello? Oh, wow.
Yeah.
Yeah, so I do a fair bout of linguistics research as well, and the problem is finding data sets that are labeled. So what was the inspiration for breaking up the data set as you did?
The inspiration was just that I knew I wouldn't have the patience to sit down and do all of it at once.
That's a good reason. Oh.
and just that I knew that the performance is going to improve the more training data added in. So I thought I'll just start small and just see how it went. And it did indeed. I mean, so 68% was the best I did on 10% of the data. And with 20%, it quickly jumped to like 72, and then it just increased from there up to about 79%.
Oh,
so, yeah.
Thank you.
Sure.
Great. Do we have one more question?
Yeah, real quick. Sure. It was interesting your comment about having trouble yourself identifying or the origin of the word. So I think it's interesting, like, what is the human benchmark you're comparing yourself to?
Right.
Your machine learning classifier it might not look that good, but it might be pretty good compared to a human,
Right.
So, yeah.
Right. Okay, thank you.
Great.
Right.
I think that's it. Thank you very much, everyone.
Thank you. Thanks for giving me the 5